So what is the matrix? So arranging of an elements in rows and columns. So see here I am arranging some elements, that is A11, A12, A13 and A21, A22, A23 and A31, A32 and A33. I am arranging the elements in rows and as well as columns. So this is the number of rows and this is the number of columns. So that is, here we are having, first one is indicated with the rows and second one is indicated with the columns. Okay. So how we have to add a 2 matrix or else subtract a 2 matrix or else multiply a 2 matrix. So let's say consider a 2 by 2 matrix of a matrix 1, 2, 3, 4. So this is a 2 by 2 matrix, 2 rows and 2 columns. So similarly I am considering a V with a 2 by 2 matrix. Simple example, 2 by 2 matrix is a basic thing. So I am adding a plus B. So what we have to do, we have to add the individual element. So that is 1 plus 1 1 plus 1, next 2 plus 2, 3 plus 0 and 4 plus 0. See, if we have to add a 2 matrix A plus B, the order should be equal. If this order and this order is not equal, we cannot add those things. Why? Because if we consider 1, 2, 3, 4, next you are considering 1, 2, 3, 4, 5, 6. So this is an order of 2 by 2 and this is an order of 2 by 3. If we want to add this, we can add up to here. But what about this? We are not having another column here. So that's why it is not possible. So what we can say that addition of a matrix is possible. So addition of a matrix is possible if and only if the matrix order should be equal. Orders of 2 matrices should be equal. So this is very important. If this is not equal, we can't add the 2 matrices. So in the next case, in the subtraction also is in the same fashion. Whereas coming to the multiplication, A into B, right? So here is a quite different and logistical way. In previous case, we have to equate the matrix order, rows and columns as exactly equal. But here, the first matrix column should be equal to the second row. So see here, this is the first matrix column. This is the second matrix row F. This number of columns of the first matrix should be exactly equal with the rows. So then we can make the possibility. Row into column. Similarly, so that is first is 1 into 1 plus 2 into 0. This is the first element. Then the second element is 1 into 2 plus 2 into 0. This is the second element. So whereas coming to the third element, 3 into 1 plus this row and this column plus 0 into 4. Similarly, finally 3 into 2 plus 0 into 4. This is the last. If the rows and columns are not equal, we can't do the multiplication. Why? Because so number of rows is multiplied with the number of columns. So we have to consider this column is exactly equal to this number of rows. Then the matrix is final matrix is 2 by 2. So this is 2 and this is 2. Here it is not a problem because we are doing the square matrix. But whereas coming to the triangular matrix, this is 2 by 3 and another matrix with a 3 by 2. So if we want to multiply these two A by B matrix, A into B matrix. So these columns and these rows is exactly equal. Finally we are getting the matrix of 2 by 2. Order has been changing to the matrix of. So Matrices are classified into different types. In those things, first of all, we have to tell about the square matrix and triangular matrix. So in the matrix, the number of rows. So what are the number of rows is not equal to number of columns. For example, consider these things. So this is 1, 2, 3, 4, 5, 6. So here, the number of rows are 2. Whereas coming to the number of columns are 3. So number of rows is not equal to the number of columns. So that is called as triangular matrix. So whereas coming to the square matrix, the number of rows is exactly equal with the number of columns. So for example, consider this matrix. So in this we are having totally 3 rows and 3 columns. That is, this is a 3 by 3 matrix. So number of rows is exactly equal with the number of columns. So after these two classifications, we are having the scalar matrix. So in the scalar matrix, we are dividing the entire matrix into principal diagonal elements, so above the diagonal elements and below the diagonal elements. So in this, the diagonal elements are having some value. Those diagonal elements will be equal. So that is lambda, lambda, lambda above the diagonal element and below the diagonal elements. Remaining things all are 0. So in the identity matrix, so the diagonal element should be equal. That should be 1. So that should be 1, 1, 1, 1. So remaining value should be 0. So and the trace of the matrix. So we have to find out the trace. The trace is nothing but the sum of the diagonal elements. So that is sigma is equal to I is equal to 1 to n aii. So that is a11 plus a12 a22 plus a33 and so on up to n times. So this is the trace of the matrix. So whereas so these are the sum of the properties for the trace matrix. Trace of Ka is equal to K into trace A. So let's see how it will be happen. So this is 1, 2 and 3. This is some 3, 6, 5, 2, 4, 5. So this is the trace, that is 1 plus 2 plus 3. That is 6. If I am multiplying with some 2 factor, so it is multiplied with each and every term. So that is 2, 6, 12, again 10, 4, 4, 8, 10 and 6. So now add these things. 2 plus 4 plus 6, that is equal to 12. So if I see here, it is multiplying each term. So now I am writing that the product K2 into 6, that is nothing but 12. Previously we are getting the 6 value, so now I am multiplying this with the 12. So the first property will be valid. So whenever the trace of a K matrix, it is exactly equal with the K into trace of particular A matrix. If you are considering the trace of 2 matrices adding of sum of the 2 matrices, find out in those trace is nothing but trace of individual matrix summation. Similarly, trace of AB is exactly equal with the trace of B. So because we know that AB matrix is exactly equal with the BA matrix, right? So now transpose of the matrix, rows interchange to columns and columns interchange to rows. So see here, A is 1, 2, 3, 4. If I am changing the entire rows to the column 1, 2, I am changing the columns to the rows. So rows 1, 2 and 3, 4 is interchanged. Similarly, columns 1, 3 and 2, 4 are interchanged to rows. So rows is interchanged to column and column is interchanged to row. Here also we are having the property A transpose of O transpose is nothing but A. So because if again I am interchanging these things, the A transpose will be occur. This is one first property. So A into B whole transpose is equal to B transpose into A transpose. So if you cross check these two things, it also happens there. Similarly, A plus B whole transpose is nothing but A transpose into A transpose plus B transpose. So these are the sum of different another matrix. So matrices. So idempotent is nothing but the matrix of A square is equal to A. If any matrix having some matrix value A of R m by n. So if I am doing the square of those matrices, if I am multiplying A into A, right? If I am multiplying A into A, that is A square. If again the same matrix will occur, that is called as idempotent. Nilpotent. So what you mean by nilpotent? So nil means itself says that is a 0, right? If any matrix is multiplied to the power of n, that is suppose example A square or A cube, something A power 4, anything may be, if that value may be equal to 0, that is termed as nilpotent, and the m is indicated as index of nilpotent. So index of nilpotent, right? So inverted. So in the inverted matrix, it is nothing but the identity matrix. We are having the identity matrix is 1 0 0 1 for 2 by 2 matrix. So if it is equal to identity matrix, it is an inverted matrix. So conjugate matrix. So what is a complex conjugate? So whenever A plus I is equal to, so A plus IB is a complex value. The complex conjugate of A plus I is nothing but A plus IB is equal is the complex value. What is the conjugate value? Complex conjugate value A minus I. If a matrix having some conjugate values, complex conjugate values, if you are doing the complex conjugate to the particular matrix is nothing but the conjugate matrix. See here 1 plus I, so 1 plus I, 2I, 3 minus I. If you are doing the complex conjugate to that is 1 minus I, minus 2I, 3 plus I. This is the complex conjugate matrix. So why we have to do these things? Let me discuss about this.